Okay, this video is looking at collision theory. It's based on chapter 7.2. You need to be able to know what these words are and use them correctly. And also we're looking at energy profile diagrams again, and another graph looking at the amount of energy different particles have and their relationship to activation energy. Alright, collision theory, you need to know this definition off by heart. So it's in order for a successful reaction to occur, the reaction particles must collide with each other with enough energy to overcome the activation energy, so break the bonds, and in the correct orientation. So you need to be able to break this down if you have to. Successful collisions. Most collisions aren't successful, so when particles, the reactants collide, nothing happens. So they have to have enough energy to break the bonds, and they have to be in the correct orientation. So the more successful collisions you have in a set period of time, the faster the rate. Or instead of using set period of time, if you use the word frequency, it means how often something happens in a set period of time. So the rate of a reaction depends on three things: the frequency of collisions, how often the reactant particles collide, the amount of energy that they collide with, and if they're in the correct orientation. So we're going to look individually at each of these three things, and there will be headings at the top of the page, so depending on which one we're looking at. I'd like to acknowledge that the following video comes from this website. Okay, we'll let this play through once. Notice where the particles form, and then we'll play it again to see the collisions. It's at 11 degrees. Okay, we'll do it again. Notice these particles here and this one here. When they meet right at the beginning, they're going to form the first product. So if we started, so we've only gone for 1 second now, and those particles have already formed. So it only forms 4 products in the first 10 seconds, and already in the first second it's formed 2 of those 10. Now if you look at these particles here and this one here, you notice if I go back, they're colliding but nothing's happening. And when you move over here, there's a collision between these two, but nothing is happening. So they don't have enough energy to break their bonds to react. So even though they collide, nothing happens. Okay. Then the next collision is down the bottom there, and then the last one, you have to wait for quite a while before you get another one, and right at the very end we get another one here. Okay, so it shows you that when the particles has a higher concentration at the beginning, you get a higher rate of reaction right at the beginning, and then the rate starts to slow down. Also, when not all the particles that collide will result in a successful breaking of bonds in a collision. So there were 4 different factors which affect the rate: concentration and surface area. If you remember these two together, because they're both basically looking at how to speed up the frequency of collisions. Temperature also makes particles move faster, so it speeds up the frequency of collisions, but it also affects the energy that particles collide at, and catalysts lower the energy that's needed. So we're going to look at the frequency of collisions first for these first 3. The rate is determined by the number of successful collisions in a set period of time. Any factor which increases the number of collisions in that time, so the frequency, will also increase the number of successful collisions. So the more collisions that you have, the more likely that some of them will be successful. So if the proportion stays the same, then if you have more, you'll have more overall. So it's probably good to do an example. If you've got 100 reactant particles are colliding every minute,
and about 20 of these collisions are successful, then the proportion is about 20 to 100. So about 20 successful collisions out of the 100 per minute. If you did something to speed up the collisions that you have per minute, so maybe if you increase the concentration, if it was increased, then you might double the number of collisions that are happening per minute. So if it's still 20 for every 100 and you've got 200 a minute now, then you would have 40 successful collisions per minute. So you don't have to, this is the proportion, out of every 100 you have 20. So this is not changing the proportion, it's just changing how many totally that you have. So that's what frequency means. Okay, so if the things that we looked at, those three affect, if you change those, they will change the frequency. So they change the number of collisions and therefore the number of successful collisions as well. So if we look at concentration, we've got reactant particles. You need to know what concentration means. It doesn't mean that there necessarily are more particles, it just means how close together they are. And so the closer together they are, the more that they are going, the faster they're going to collide with each other. So if you arrange them in order, the higher the concentration, the faster the rate. Why does concentration increase the rate? Because if the particles are closer together, then they're more likely to collide. So this increases the frequency, how often they collide per period of time. Surface area, same thing. This video is looking at the boardworks PowerPoint. So they showed animations on this. So they started this animation. When we started it was counted down from 15 seconds down to 0, and it showed the number. If this was one reactant and these are the other reactants that have to meet in order for a reaction to happen, if you break that solid reactant up, you now have places, all these extra surfaces that the particles can collide. So they showed the particles colliding, and then when it counted down to 0, it added up the number of collisions. So you can see when you've got all this extra surface, then the number of collisions is much faster, much more collisions, so therefore much faster rate. Okay, so that was concentration. Okay, so now we're looking at temperature, and this proportion also plays a part in the temperature and catalysts. So proportion, this is talking about the amount of energy that different particles have to overcome the activation energy. If you see this, it means the activation energy, the energy that you need to break the bonds. So if particles collide with less energy than the energy needed, they not react, they'll just bounce off each other. So we've looked at energy profile diagrams before. This is the activation energy. So it means that if you've got this particular reaction, hydrogen and iodine reacting to form hydrogen iodide, the bonds have to break between the iodine atoms and the hydrogen atoms. So the activation energy is when the bonds here have broken. And then they need to reform to form hydrogen here, iodide. So this is a transition state when there are actually no bonds between any of the atoms. And then when the bonds reform, energy is released here at this point, and they have formed new bonds. So the activation energy is when you're breaking the bonds, you're adding energy to break the bonds, and this is the energy that's forming, being released when new bonds are formed. So this is an endothermic reaction because not as much energy was released as was taken in, so the products have more energy in them than the reactants, and it's positive if the products have a higher number than the reactants. Okay, in the textbook it's showing that the activation energy for different reactions is different. So this particular one, you need a tiny amount of energy to break the bonds. This is nitroglycerin. It's an explosive. So you only have to kind of bump this and it will get enough energy to break the bonds, and it forms, you notice that this nitroglycerin is a liquid, and when it reacts it forms all of these 10, 12, 22, 28, 29 moles for 4 moles of, and they're all gases. So that's why nitroglycerin is an explosive. So the activation energy is different for different sorts of reactions, and the smaller the activation energy, the faster the rate of a reaction will be. Okay, this has been heated up, so it's at 20 degrees. So we're going to look at the products again. Remember, the products are in red, for another 10 seconds. Remember, at a higher temperature, two things happen. The particles will be moving faster, so there'll be more collisions generally. So there'll be a greater frequency of collisions in more collisions in a set period of time. So our set time that we're looking at is 10 seconds. So rather than saying how many collisions in a set period of time, we can just say there's a greater frequency of collisions. And more of those collisions are going to be successful, because when you have more energy, when the temperature is higher, then more of the particles, a greater proportion of the particles, will have enough energy to break their bonds when they collide and so react. Okay, so we'll play it. So you can see already in 5 seconds there is already 4 particles produced, whereas at 11 degrees it took 10 seconds to get the 4 products produced. So we've got more products produced in the 10 seconds in the set period of time. So there was a greater frequency. You might have noticed that the particles were moving faster than at 11 degrees, and more of them have been successful. Okay, so this is still at 20 degrees, but there are more particles, so the concentration of the particles is higher. So there are more particles, they're closer together, so there's going to be a greater frequency of collisions. The proportion will be the same, but there will be a greater frequency, so the rate will be faster. So we'll just play this for our 10 seconds, our set period of time. And so you would be predicting that there would be more than 12 products, because you have increased the frequency as well as, so the proportion is the same. So the proportion of particles that of the collisions, the proportion of particles that have got enough energy will be the same, but there's just going to be more collisions in the set period of time, so greater frequency. Okay, with only a small amount of energy. This is a new graph that we're looking at. It's looking at all of the particles at a particular temperature. They don't all have the same amount of energy. So if we piled up all the particles, so a number of particles, so pretend it's like a whole lot of sand, all the particles, you pile them all up. Most of the particles will have this amount of energy, and this small amount here will have a small amount of energy, and these particles all here will have more energy. So when you say something's at 25 degrees, what you mean is that the average energy is 25 degrees. So for this particular diagram, for this particular reaction, you would need this amount of energy for the particles to react. So all of the particles past this amount of energy have enough energy when they collide to break their bonds. If we got the same particles and looked at them at different temperatures, so if we thought of it as a pile of sand again, if we take that pile of sand and heat it, then obviously the height will have to come down, because all of the grains have spread out here. So the average energy is 1,000 degrees, but you've got some particles with a lot more, some particles with less. So if we looked at the activation energy, if you've heated up particles, sometimes you don't really need to add much more heat. You don't need the temperature to rise all that much. So it's only gone up 10 degrees, this particular example, but the number of particles has nearly doubled the number of particles that can react. So the rate would nearly double. Okay, so as well as frequency of collisions, so concentration, surface area and temperature making particles collide more often, and the proportion based on the amount of energy they have, when particles collide they have to collide with the correct orientation. So this is showing hydrogen iodide. Two hydrogen iodide molecules can reverse and form hydrogen molecules and iodine molecules. So hydrogen's the smaller atoms, iodine the larger atoms. So in order to form two hydrogens together and two iodines together, the hydrogen iodide molecules have to collide in the correct orientation, so the hydrogens have to be next to each other. So this orientation is unlikely to result in a reaction, but this orientation is likely. So after all of this, pause this. Could you answer this? Do you have the language to answer this question? Okay.